Hello, my name is Jonggyu Park. I'm from Sungkyunkwan University. Today I'm going to talk about the fragmentation problem on flash Optane storage devices and a new solution to address the problem. Fragmentation is a phenomenon where file blocks are scattered across multiple non-contiguous areas. It is commonly called as file fragmentation, file system fragmentation, and file system aging. Traditionally, we believe this significantly degrades the I/O performance since it increases the seek time of the underlying storage devices. So what we can do is performing defragmentation like this. Many people think fragmentation is no longer a problem on modern storage devices because they don't have seek time. I'm not sure about it. Let's Google it. This shows the number of publications on Google Scholar when I search file fragmentation. Seems like the number is decreasing recently. And let's add flash here. It seems like fragmentation is really not a big problem on flash storage. How about Optane devices? I will replace flash with Optane here. This is not accurate because it requires the exact keyword file fragmentation instead of other names, but we can guess researchers don't care about fragmentation recently. Fragmentation. Is the case really closed? Let's ask about it to the SSD vendors. I think they can answer the question well. Samsung says SSDs do not require defragmentation, and Intel says so, and even recommends disabling automatic defragmentation because it adds unnecessary wear. Finally, SK hynix also says the same thing and additionally explains the reason. It says SSDs do not find data in a mechanical way unlike hard disk drives. For sure? Some researchers still argue that fragmentation matters on flash storage. Previous research observed that fragmentation matters in mobile devices and it happens again quickly even after defragmentation. Another researcher found that fragmentation significantly degrades the performance of flash SSDs on major file systems such as ext4 and FTFS and BTRFS. They replayed the problems using Git scenario. More recently, another study experimentally demonstrated that the performance of file systems in the paper are actually different from the reality because of file system aging. Finally, another paper argues that fragmentation really occurs on even clean SSDs, and they said regarding fragmentation, the usage is more important than fullness. But the SSD vendor said fragmentation is nothing because such devices have no mechanical moving parts. Let's look into the Linux I/O path. Suppose that a process issues a read operation, it goes through usual level library and is delivered to the kernel via system call. And in the file system layer, file system investigate the sequentiality of LBA of the read operation because file systems view data in terms of LBA while applications view data using file offset. If it's not sequential, request splitting occurs. Here, request splitting means a single system call is divided into multiple I/O requests. The problem of request splitting is that it increases the number of I/Os and makes the I/O smaller and increase their randomness. This significantly affects I/O activities throughout the entire I/O stack. Afterwards, the I/Os experience the block layer which performs request creation, queue insertion, merge, sort, staging for scheduling, and even dispatching. And then I/Os are transferred to the storage through I/O interfaces, and finally the corresponding data will be fetched from the storage chips. SSDs utilize multiple parallel units to maximize I/O performance. However, fragmentation decreases the size of I/Os and increases their randomness, which hinders efficient utilization of internal storage resources. Like this, fragmentation significantly increases kernel overheads, interface overheads, and resource conflicts inside the storage. To verify request splitting is the main problem, we perform some experiments. Here we utilize new terminology, frag size and frag distance. Frag size denotes the size of each fragment, and frag distance means the distance between two fragments. We also utilize a statistical methodology here. Correlation coefficient means how related the value is to the performance, and linear regression slope shows how significantly the value influences the performance. It means that higher CC and NLRS means the value is critical to the performance. We executed 128 kilobyte sequential reads on F2F file system with various frag size and frag distance. Here we utilized direct I/O to bypass kernel page cache. Since the request size is 128 kilobyte, request splitting occurs only when frag size is smaller than 128 kilobyte. In the case of hard disk drives, the performance gradually increases along with the frag size, and the performance decreases when the frag distance increases. A longer frag distance means hard disk drive requires more time locating its mechanical part on the corresponding data location. This result denotes that the performance of hard disk drive is sensitive to both frag size and frag distance. This is because of its seek time. On the other hand, none of flash and Optane storage is sensitive to frag distance because they do not have seek time. Instead, they are sensitive to frag size until the frag size becomes the request size. After that, the performance gain gets smaller. This means request splitting is critical to the performance of modern storage devices. From these experiments, we can guess that the performance of modern storage devices mostly depends on the occurrence of request splitting and is irrelevant to the distance between fragments. Let's take a look at the conventional defragmentation tools. First of all, they are file system dependent. Since each file system has its own block allocation policy, they require their own defragmentation tool to change the location of existing data. For example, exe4 and XFS adopts in-place update, while F2FS and BTRFS utilize out-place update. So exe4 has its own defragmentation tool called e4defrag, while BTRFS also has its own tool. Second, the conventional tools are designed under the assumption that the underlying storage device have seek time. Therefore, they migrate the entire contents of data, which significantly degrades the performance of core running applications. Third, modern storage devices have a limited lifespan. Therefore, the additional bulk writes incurred by defragmentation reduce their lifetime. Finally, it is really time consuming. Therefore, people are actually afraid of using defragmentation. In this paper, we attempt to mitigate such problems. First, we now know frag distance is not important to the performance of modern storage devices according to the previous experiment. So, let's just ignore frag distance and do our best to prevent request splitting. What we can do here is this. Let's partially migrate certain data, not all the data. But the problem is, we need to decide which data to migrate and how to migrate. To find out the optimal pieces of data for migration, FragPicker performs I/O analysis. Additionally, FragPicker utilizes some techniques to perform file system agnostic migration while minimizing the amount of writes. To achieve this, FragPicker performs mainly two tasks. First, the analysis phase consists of system call monitoring, per-file analysis, and hotness filtering. System call monitoring gathers I/O information at the system call layer, and per-file analysis analyzes the I/O characteristics for each file. Hotness filtering removes unnecessary pieces of data to minimize the amount of writes for defragmentation. The migration phase consists of fragmentation checking, block location, data migration. First, the migration phase checks the fragmentation state of each piece of data to further minimize migration data. Afterward, FragPicker allocates a new contiguous area and migrates fragmented data into the newly allocated area. This is what the analysis phase does in detail. First, FragPicker monitors the system call layer and extracts necessary information using BCC. BCC is a toolkit for efficient kernel tracing, making use of extended Berkeley packet filters. Using BCC, we extract request type, if the I/O is read or write, an inode number, and the I/O size, start offset, and finally, whether or not the I/O is direct I/O. Afterwards, FragPicker performs per file analysis. In this process, it creates per file range list, which includes start offset, end offset, and the I/O count for each range. And then, it adjusts the file range to be aligned with file system blocks. It's because later, FragPicker performs deallocation of file system blocks, and the current implementation of deallocation removes any data that are not aligned with file system blocks. Afterwards, FragPicker investigates if the I/Os are in sequential buffered read or not. If they are sequential buffered read, FragPicker manipulates the file range list to reflect the read-ahead mechanism. Since the kernel read-ahead is applied under the system call layer, FragPicker should mimic the read-ahead mechanism by itself. Finally, it merges overlapped I/Os and calculates the I/O count. Without merge process, the overlapped I/O ranges can incur another fragmentation after migration, like this. Therefore, we merge such ranges like this. The hotness filtering truncates the file range list according to the hotness threshold. In the per file analysis, FragPicker calculates the I/O count for each range. Using the I/O count, FragPicker only keeps hot data regions that are frequently accessed. In other words, this process removes unnecessary pieces of data that are not critical to the performance. The migration phase utilizes the per file range lists that are obtained from the previous analysis phase. First, FragPicker performs fragmentation checking against each chunk in the file range list. Here, the chunk 1 is fragmented, so it needs migration. However, the third one is actually contiguous, so migrating it creates unnecessary writes without any performance gain. Therefore, we keep this as it is. And chunk 4 is also fragmented and thus needs migration. Like this process checks the fragmentation state of each range and decides which one to migrate in order to further minimize the amount of writes for defragmentation. Afterwards, FragPicker performs block location. In the case of outplace update file systems, simply updating the data on the same file offset will change the data location. However, in the case of in-place update file systems, explicit block location is necessary for data migration. Therefore, using fallocate, we allocate a new contiguous area in advance to migration. The block location consists of deallocation and allocation. First, FragPicker deallocates the existing data using fallocate's punch hole and temporarily store the corresponding data in in-memory buffer. Afterwards, FragPicker allocates a new contiguous area for further migration. And then, it migrates the data by writing them from the buffer to the new area in the next step. Deallocation performs zeroing data that are not aligned with the file system blocks to prevent falsely reading data. However, since the per file analysis step already adjusted the file ranges to align them with the file system blocks, deallocation of FragPicker does not zero any of the existing data, which means FragPicker can recover the data upon system crash. Here, since outplace update file systems do not require block location, FragPicker skips this process in that case. Finally, data migration is performed using user-level I/O libraries. After defragmentation, performance-critical data become contiguous, and I/Os towards such data will not incur request splitting. Since the chunk 2 is not on the file range list, we think the data are not actually performance-critical. Therefore, FragPicker does not migrate the data. As you can see, the frag distance can actually increase after defragmentation of FragPicker. However, as we saw before, frag distance is irrelevant to the performance of modern storage devices. To evaluate FragPicker, we use two different kinds of SSDs, one for flash and one for Optane. First, we generate fragmented files and execute various workloads using the files and measure the I/O performance. Afterwards, we perform defragmentation and calculate the amount of writes during defragmentation and measure the I/O performance again. We utilize 4 different kinds of workloads: sequential read and update, and straight read and update. In these experiments, we want to know if FragPicker can really reduce the amount of writes for defragmentation, and if it can achieve a similar level of performance gain compared with conventional tools. We utilize 3 different kinds of major file systems and their defragmentation tools: ext4, ftfs, and btrfs. Since ftfs does not have user-friendly tools, we built a new one by mimicking other tools. Here, FragPicker B bypasses the analysis phase and automatically creates the analysis results under an assumption that the applications issue sequential IOs. The experimental results show FragPicker actually does reduce the amount of writes for defragmentation. In the case of sequential IOs, FragPicker shows around 50% less writes and 75% less in the case of straight workloads. This reduction in the amount of writes is because the analysis phase of FragPicker effectively finds out the optimal pieces of data for migration, and fragmentation checking of the migration phase further minimizes unnecessary writes. In terms of performance, FragPicker improves both sequential and straight performance by around 30% and 42%. And in the case of straight reads, FragPicker even outperforms the conventional ones. FragPicker migrates the fragmented data in the way the data are actually accessed. Therefore, FragPicker can place the data in a better way than migrating the entire contents in a sequential manner. In the case of Optane SSD, FragPicker could achieve around 120% performance improvement at most. It is because Optane SSD is a high-performance storage device, and the additional kernel overheads caused by request splitting is more noticeable. Here, in the case of sequential reads, the performance gap between FragPicker and E4defrag shows only around 0.1%, while FragPicker reduces amount of writes by approximately 50%. Our paper presents more experiments, including database and file server workloads. Additionally, we also tested how sensitive the hardness threshold is to both the performance and the amount of writes in our paper. In the real world, SSD are diverse. Their internal FTL implementation varies depending on the vendors and models. For example, one can adopt a different prefetching policy or different mapping policy. Such differences make different performance characteristics. Therefore, some SSDs might benefit from bigger contiguous blocks than the request size, depending on internal prefetching policies. In our experiments, we observed that just placing data in a sequential manner is not the best solution on some workloads. Therefore, we think FragPicker can be utilized for not only defragmentation, but also better data placement according to the application I/O characteristics. But the best data placement to exploit maximum performance is different depending on the devices. I think it will be interesting to standardize such things using various metrics. In conclusion, FragPicker is a new defragmentation tool for modern storage devices. Thanks to the existing tools, it requires no kernel modification and is file system agnostic. The file system agnostic attribute of FragPicker can help new file systems in progress evaluate the fragmentation, defragmentation effect, especially regarding aging test. Additionally, conventional file systems that do not have user-friendly defragmenters, such as FTFS, can readily utilize FragPicker. FragPicker requires the systems to support eBPF and consistency in the file system layer, and allocate and file frag program. Finally, it needs the file system ability to provide a contiguous LBA region for a single write operation, since FragPicker relies on user-level I/O libraries for data migration. Thank you for listening to our presentation. The source code of FragPicker is available here. If you have any questions or suggestions, you're welcome to contact us.